Okay, good afternoon. Thanks for the invitation. Thanks a lot. I'm really happy.
Sorry, you have to accept the recording.
I did on my computer, but also here.
Yeah, probably, yeah. Sorry for that.
Wait.
Got it. No, don't even. Got it. Okay.
Okay. So I will talk about Poisson gauge theory. This is a work in collaboration with Vladislav Upiano from São Paulo, Brazil, and Max Kurkov from my department. I will first explain what do I mean by Poisson gauge theory. Then I will motivate why are we interested in looking at this kind of theories. So a Poisson gauge theory is simply a gauge theory where space-time is a Poisson manifold. Namely, there is a non-trivial Poisson bracket on space-time. And we ask whether and how we should modify the usual approach to gauge theory in order to be compatible with this underlying structure of space-time.
There is some really strange clicking on the Zoom session. Can you hear that as well, Peter?
No, I can't do that. Everyone is muted, all the participants.
Okay, so there's no extra sound for you. Depending on this laptop, then that's okay.
So the outline of the book. I start with commutative field theory. Why that? Because manifolds with a Poisson structure can be seen as the semi-classical limit of a non-commutative space-time. So one main motivation for looking at field and gauge theories on a Poisson manifold is non-commutative field and gauge theory. They are kind of semi-classical approximation to non-commutative field theory. So I will say in the following something about non-commutative field theory, because I suppose not all of you are working on that. Motivations for non-commutative geometry are non-commutative field theory are essentially related to the fact that in many approaches to quantum gravity, one sees discreteness of space-time emerging. And this is implicit when you do non-commutative geometry, because your space-time is non-commutative, and then you have a minimal area in space-time under which you cannot do measurements. One typical argument for being interested in non-commutative field theory is the conjugation of the general relativity point of view with quantum mechanics. And one of the oldest motivations for this space-time non-commutativity, which goes back to the fathers of quantum mechanics, is the attempt to regularize in the ultraviolet quantum field theories. There are many approaches to non-commutative field theory. There is no general consensus about what should be the right one. There are many drawbacks, but the problems that the theory wants to address are still there, and they are still valid. So here the approach we choose to follow is based on two requests, namely a formulation which gives back the standard commutative limit. We don't want a deviation from the usual commutative limit. And then we also want that the algebra of gauge transformations, of gauge parameters is a closed algebra with respect to the non-commutative structure. So let me start with a review of non-commutative. Well, here I write QED, even though I will not touch the quantum spectrum, only non-commutative, which doesn't mean quantum. If you want, you have two quantization scales. One is space-time quantization, the other one is usual H-bar quantization. So here we are only looking at space-time quantization. So one approach to non-commutative, standard non-commutative gauge theories is to start with a non-commutative algebra, which replaces space-time, because now space-time is not a manifold anymore. So you replace it with the algebra of operators on it, that you can in turn represent as the algebra of functions on the old space-time with a non-commutative star product. This product that I have here, the star. Then fields. Matter fields are usually vectors. They are sections of some vector bundle. Vector bundle needs an underlying base manifold. Here there is no base manifold anymore because we are non-commutative. So the vector bundle is replaced by a module over the algebra of non-commutative functions, which is replacing space-time. So this A will be the algebra of non-commutative functions, which is replacing space-time. Then we have gauge transformations. Gauge transformations, namely maps from the space-time into the group that we are considering. Here will be replaced by unitary photomorphisms of the module. They act on field. Then the dynamics of fields. So in order to describe the dynamics of fields, we need derivations. We need a differential calculus which is compatible with this non-commutative structure. Compatible meaning, we will see it in a moment, that simply the Leibniz rule will hold with respect to the star product that we have here. The gauge connection will simply be a natural analog of the standard linear connection on vector bundles. So the first problem one has to address in this approach to non-commutative field theory is to have a well-defined differential calculus. Namely, as I was saying, essentially you need that the derivations that you have fulfill the Leibniz rule. So let's start from the well-known and very much studied case of the Moyal non-commutative space. What it is? Well, it is the algebra of non-commutative functions on R2n. I choose here to work with even dimensions, but it is not mandatory. You can also live with odd dimensions. This is modeled on the phase space of quantum mechanics, meaning that the non-commutativity is constant. So the difference, of course, they are similar formally, but the difference here is that we are quantizing space-time, whereas in quantum mechanics you quantize space-space. So the non-commutative product, which is meaning the non-commutativity of operators depending on positions, is this star product here. This one is an asymptotic form of it. There is a closed form, but we don't need it. And if you apply it to coordinate functions, xmi, now R2 and space, you see that you get a constant non-zero star commutator between coordinates. Star commutator means x mi star x mi minus x mi star x mi using this product here. The link between quantum mechanics is clear here because you can diagonalize this constant matrix here and you can really put it into a form of delta ij with half of the position coordinates play the role of the q's in quantum mechanics, the other half plays the role of the p's. And it is only formal. So this is the easiest kind of non-commutativity that you can have on your space-time. P has the dimension of an area, so this would represent the minimal area in your space-time below which measurements are not allowed. So the concept of points loses its significance. So here you have a minimal set of derivations, yes?
I don't know the meaning of the index and stuff.
This one? This one means that I am computing x mi star x mi using this one minus x mi star x mi again using this one. This of course can be represented in terms of operators on the Hilbert space, and then it will be an operator. So as I was saying, this algebra, so this is a non-commutative algebra of functions over space-time. There are derivations, namely objects which respect the Leibniz rule, and they are standard derivations in R2n. In this case, yes.
Why do you need space-time to be even dimensional?
I do not need it even. It's simply a simplification here, but I mean it is easier in this way because then theta is non-degenerate. If you are odd, theta is degenerate, then you have to say how to manage it. In quantum mechanics, phase space is always even. So this would be the perfect analog of quantum mechanics. But it can be even, it can be odd, and indeed often one has odd non-commutative spacetimes. So I was saying here it is easy to check that this one is a derivation of the subproduct, namely that it respects the Leibniz rule. It is not at all obvious you should use this expression here to check it, but it is easy to check because you can show that d by dx b can be expressed as a star commutator of the function with the coordinate, and then the Leibniz rule is guaranteed because we have a commutator, a star commutator. So this is the Moyal algebra. What? Okay, this is why I don't know why. I hope there was nothing before. Anyway, but this is page 6. Sorry. This one page is missing. Sorry, let me see what happened to the file. Well, something went wrong with that page, I don't know why.
No, it seems page 5 is just blank.
Sorry?
Page 5 seems to be
Yeah, but
blank.
it shouldn't.
Yeah.
Here it is. This is page 5. So what can I do in order to show it again?
You can go to full screen probably.
But here I am in. So let me do this.
This is combining.
Okay. Now,
green one.
sorry, I open again the PDF. And I go to page 5, formulate tools. No, it doesn't.
You could probably go to full screen on this.
But this is in Tech Shop. Can I go to full
I
screen
imagine
here?
so. I don't see why not.
I think the green dot will do.
Then?
Just click on the green. It's covered now. The
Here?
top left.
You click on the main page.
Okay.
Yeah, now that will. What's on the page?
Can you see from home? From remote? Yes?
Yeah.
Okay, maybe I will stay with this and then
Okay.
I try to make it big.
The bottom of your slide is cut out, but I think that's for everyone.
Sorry, what did you say?
I think
Yes,
it's okay.
some of your slide is gone up, but you can scroll up and down.
Okay.
When you get to it, you can
Yeah.
show it.
Okay, so we were saying so I showed you what is the Moyal algebra. Now, what is a gauge theory on this space in this approach? So by ED, I mean electrodynamics, meaning that my gauge group is U1. The hat means that I am considering the gauge group, namely maps from my space-time into U1. So what are charged matter fields in this case? They are one-dimensional complex vector fields, sections of one-dimensional complex vector bundle, namely, so the analog, the non-commutative generalization would be a one-dimensional complex right module, meaning that we have only one generator. This C here is the module, and this is the non-commutative algebra of functions. So fields in this case are represented by non-commutative functions over this R2n theta space. There are some mathematical details that we are not, we will not need in the following. For example, the Hermitian structure. The generator of this one-dimensional module, I am calling it 1. And the gauge connection is defined as usual, namely, it is by definition the value of the covariant derivative over this one generator that I have. I call it A. So A is the one-form connection, which is defined in this way as the value of the connection over the generator. Meaning that when we act on matter fields, we get the usual expression. So the covariant derivative of a matter field is a derivative plus this term here, which now you notice I have a star product. Both A, M, and C are non-commutative functions.
Okay, ninth question. How do I think of field configuration? And what would be the analog of section of the vector bundle here?
So the vector bundle would be exactly this structure here. Your fiber in the vector bundle is one-dimensional complex because the gauge, the group is U1. You only have one generator, and then the connection is doing exactly what I wrote here. Namely, it is realizing the interaction between the matter fields and the radiation fields. It is modifying the derivative in your space in this way.
I mean, there is no base space.
Here, there is no base space. That's why I do not speak about vector bundles, but I speak about modules over the algebra non-commutative functions. There is no base space here.
I mean, is there a naive way to picturize the thing? I mean, how do I think of it? It's quite mathematical.
Well, maybe it becomes easier once I have given all these definitions. We will see in practice how the gauge theory
Well, you
looks
can,
like.
you can still think of it in terms of your usual picture, because if you think of your theta as a small parameter, you can see that it's still the gauge theory picture. It's exactly the same familiar section on.
So theta equals to 0, yes.
No, but I mean the usual
parameters.
gauge theory, classical gauge theory in terms of vector bundles, it is exactly a right module over commutative functions in that case. So once you have redefined your classical gauge theory in this way, it is easy to replace in this way. This could be the translation of geometric objects into algebraic objects in the standard gauge theory, and then you simply replace this algebraic picture with the non-commutative analog. But it is really exactly the same. So the only difference being that while here you can go from here to here to the geometric underlying picture, here there is no geometric underlying picture because there is no space-time. That's why you are dualizing, you are making it algebraic.
I think you can still think of the underlying geometrical picture not having changed, in the same sense that if you're familiar with quantum mechanics and phase space.
Well, phase space,
there's no underlying geometrical
there is no manifold.
There's no manifold, but you can still think of it.
If you think, so you already are familiar with a non-commutative geometry. It is only that you are so used to work with it that you don't realize that in that case you do not have a manifold. Quantum phase space is not a manifold anymore because you have a minimal area and you have operators. You do not measure Q and P at the same time at the contemporary. Okay, so as I anticipated, gauge transformations are unitary automorphisms. In this case of U1 really means that they are the unitary elements of the algebra of the non-commutative algebra. Unitary elements meaning that if you multiply G dagger by G, you get star multiply, you get the unity. And this means that gauge transformations are star exponentials of functions, of non-commutative functions. A star exponential is defined in this way. It's really a series. Gauge covariance. Gauge covariance requires that the gauge connection transforms in a non-homogeneous way. So this should recall you what happens with non-abelian gauge theories. Here the situation is very similar to non-abelian gauge theory. The difference with standard U1 is that in the case of standard U1, everything commutes, so you are only left with AB, and here you would only have the derivative of a small gauge parameter. But now you have a star product, so you cannot move things around, and the gauge transformation is what you would have in the standard U1 theory plus the star commutator here, which is very similar to what happens in non-abelian gauge theory. Difference being that there you cannot move things because they are Lie algebra valued. Here you cannot move things because you have a star product. Okay, so the curvature as well gets this contribution here, which is absent in usual U1 theory, but it is in non-abelian theories. It's a different meaning again. So the gauge transformations that you get for the gauge potential and the gauge field strength look like that. And you see that this strength is covariant now, implying that you can construct a natural action which is gauge invariant because this product turns out to be cyclic. Namely, I can bring this on the other side. So for Moyal, let's say everything works, at least at a classical level, and more importantly, the algebra of gauge parameters respects the non-commutative algebra, the non-commutative underlying algebra.
And you make the simplicity of the integral of the product.
The integral is cyclic, yeah. When one says that the product is cyclic, meaning that the integral f star g is equal to the integral of this star f. This is so the two things that we wanted to keep, namely the right commutative limit and the closure of the gauge algebra, in this simple case of constant non-commutativity are there. Let me briefly look at what I mean by semi-classical limit of this theory. Semi-classical means that the product now becomes the usual commutative product, but the star commutator not. Because the first non-zero order of the star commutator is the Poisson bracket. If you go back to the, this is important because otherwise one does not understand why I'm talking about Poisson brackets. If you look at the star product here, this object here is a Poisson bracket, and so it means that the first non-zero order, not of the x, of course, but the function, x star h minus h star f only retains this term here as first order, which is the Poisson bracket of f and h. So the semi-classical picture is A and B are the usual objects for this Moyal theory. Gauge transformations are the usual gauge transformations with f gauge parameter being a function of a commutative space-time. But the gauge transformations get deformed. They have this contribution here and this contribution here, which is a Poisson bracket on my manifold, and then the closure of the algebra of gauge parameters now is with respect to the Poisson bracket. Thank you. One of the studies that work both in associative and the commutative product. This is another program.
Sorry?
The question was what not extended to non-associative and non-commutative product. There are people who do that here.
This was your question?
No, there was a question on the screen.
I see, it flashes up.
It is, I guess, in the chat.
Okay. Let's see now what's questions. From Sergio Brown. Okay, right.
Okay, maybe we can discuss again at the end.
Yes.
Okay, so, and if I perform the commutative limit, namely I send Poisson bracket to 0, I recover the usual gauge theory. So, at least for the classical non-commutative gauge theory with Moyal non-commutativity, both requests are satisfied, namely recover the standard commutative and close the gauge algebra. But this is a very special case. What now?
So you still have Bianchi identity.
I still have Bianchi identity, df is 0, yes.
So what was your answer to the question just then?
The answer to the question,
Yeah,
why not going
extending.
non-associative, non-commutative? I know that people are working with non-associative products, but here we are going one step before, namely we are not even non-commutative, we are commutative but with a non-trivial Poisson bracket. The reason for that is that the picture that I have just shown for Boyal does not work as soon as the Poisson bracket that I have on my manifold is not constant. So the question we want to answer is, what should we do in order to have a properly defined non-commutative gauge theory if the starting structure, namely the Poisson bracket that we are quantizing, is not constant. Okay? So the approach is different then from what has been done till now in non-commutative gauge theory. Why things do not work for a non-constant Poisson bracket, at least in this approach? As soon as the Poisson bracket here in pink is a function of x, the ordinary derivations violate the Leibniz rule because I have this extra factor here. And we have already seen that it is only good if theta is constant, because in that case this term will not be here and there are no other terms. But this is a special case. As soon as theta is a function of x, standard derivations are not, standard derivatives are not derivations. So for Lie algebra type star products, what do I mean for Lie algebra type star products? I mean that this theta here is a linear function of x. It is just this. And it has to be Lie algebra, namely this has to be structured constants of a Lie algebra, because otherwise the associativity is not assumed. I mean Jacobi identity. So for this kind, for this let's say the first non-trivial case, there is a generalization of the derivation-based approach that I have shown you. The generalization is this one, so my derivations would be star commutators with coordinates, and gauge models have been constructed in the approach, but the limit theta goes to 0 does not give the standard commutative theory. And there is also another problem. The differential calculus is not, I mean, the derivations, the good derivations are not enough to capture completely the dynamics. I can be more precise. So what happens, for example, in this non-commutative space, which is called R3 lambda? R3 lambda, for those of you who know basis spheres, is the space R3, which is filled with basis spheres. Namely, the non-commutativity is SU2 like xi, xj gives epsilon I, jk, xk. The problem is that if you So you can find the derivations for this star product. There is a star product which was introduced by these people in 2002. You write down a Lagrangian, a natural Lagrangian, but this Lagrangian only captures dynamics tangent to the fuzzy spheres. It is not able to capture dynamics, radial dynamics. So for sure, you will not get the standard commutative limit. Moreover, you have a model which is, let's say, simpler than the model that you would have for a gauge theory on R3. So what is the solution? What are the proposed solutions? Various solutions. For example, one could try to modify the differential calculus, and this whole activity started by Bess, Chai-Chan and collaborators relies on an object which is called the Dirichlet twist. It modifies the derivations, or you can try to modify the action functional by adding some other terms, and this is, for example, what is done by Lang and Salvo, or this famous series of papers by Gross and Penal, where they study lambda p to the fourth and the deformation of it. There are many other models and approaches to the problem. Here we choose this approach. Namely, we go back to the slide that I showed you, the semi-classical approximation, where it is evident that
excuse me? Which approach did you choose?
The one that I am going to describe now. I am going to say what is my approach.
Good.
So, my approach is look at the semi-classical approximation of the Loyal gauge theory, where we have seen that the Poisson bracket plays a role in the definition of gauge transformations. And we ask ourselves how this semi-classical structure has to be deformed. So already at that level, I ask that the commutative limit be the right one, and the algebra of gauge parameters closes under Poisson brackets. This will, I will show you, this will modify the very definition of gauge transformation and the definition of field strength in a way that is not modifying the case when theta is constant, because we have seen that when theta is constant, everything works. So how do I do this? I reinterpret the standard commutative gauge theory within symplectic geometry. Namely, I want to see explicitly what is the role of the Poisson bracket and how it is connected to the structure of the cotangent standard. And then, once I have understood the standard picture, I introduce a new symplectic form on this terrain, such that its projection of the new Poisson bracket on the space-time manifold gives me my starting Poisson bracket. Namely, I embed my non-trivial Poisson bracket over M into a Poisson bracket over the cotangent space. And then I define gauge transformations, field strength and dynamics within this modified symplectic embedding. And of course, my requests are always that the gauge algebra closes and that the commutative limit is the standard one. How much time do I have?
You can
have time. Okay, so first thing that I do is to make an effort to reinterpret the standard U1 gauge theory within symplectic embedding. And I want to show in particular that the infinitesimal gauge transformation that we know for the gauge potential, namely this one, dmf, comes from the canonical Poisson bracket on the cotangent bundle, which is this one, namely the x's have 0 Poisson bracket, the p's have 0 Poisson brackets, and they only have non-trivial bracket between p and x. Okay, and then once I have reinterpreted the infinitesimal basic transformations in this picture, it is obvious what I will do. I will modify this structure in such a way that xi xj will be my new bracket, and see how the gauge transformation has to be modified, it being it coming from a canonical transformation. Okay, so how do I proceed? My gauge potential, my gauge connection is a one form. Then I can identify it as the fiber coordinate at x of a point in the cotangent space because it is a one form. Then, as I already said, I will associate the gauge transformation with a canonical transformation generated by the gauge parameter f, and I will compute the infinitesimal gauge transformation through Poisson bracket. So first the standard setting. Where the Poisson bracket on the space-time is 0. The cotangent space T star m has the canonical split form, where lambda 0 is the Louis form, which locally is P dl Smith. The gauge fit is a local one form on M. Then it is associated with a local section of the cotangent space, namely a map that picks a point on M and associates to it a point on the cotangent space, which is locally described by x and k. Now I consider this one form here. This is a one form on the cotangent bundle. Pi is the usual projection in the bundle, so pi star will be a one form up in the cotangent bundle. Lambda 0 is the Louis form. This vanishes locally if I use the section SA, because lambda 0 by definition evaluates the section at the local fiber coordinates. So if I do SA star of lambda 0, I get A. And if I do SA star of pi star of A, I get A again. So it's SA star of CA is equal to 0. Namely, SA star fixes P to its value A. So CA vanishes exactly on the image of section. P gets fixed to its value A. Then how do I define my infinitesimal gauge transformation in this picture? I define it as the canonical Poisson bracket which I perform on the cotangent bundle. So these objects here are objects on the cotangent bundle. Then I pull them back on the base manifold N, and I compute. And so on the cotangent bundle, I have the standard canonical bracket d by dx, d by dp. I compute and I get the standard gauge transform. So I interpret the standard gauge transform as a canonical transformation of the cotangent bundle of my space-time with standard canonical bracket. And summarizing what I have done, I have embedded trivial bracket on M into this canonical bracket on this M. I have identified A with the fiber coordinate of a local section on the cotangent. I have computed the Poisson bracket of the gauge parameter of A going up to the cotangent bundle and then pulling it back to M. Here it is, of course, redundant. We know how gauge transformations look like, but it is extremely useful to generalize when we have a non-trivial Poisson bracket on M, because now we would do exactly the same thing. I forgot to check that, of course, in that picture, gauge transformations are using the other homomorphisms, namely I have a Poisson bracket for gauge parameters of M, which is trivial, and indeed they commute. So the other gauge transformations closest with respect to the Poisson bracket on M, and P, this auxiliary variable, of course, disappears from the picture. It is replaced by A. Generalization to non-trivial Poisson bracket and symplectic embedding. So now we have not anymore theta equals 0, but we have the first non-trivial order of the star commutator, which is a non-trivial Poisson bracket. This symplectic embedding approach that I'm going to describe is a generalization of what is called a symplectic realization due to Weinstein in the 80s. And the approach that I am describing now is due to Prianov and Sabo a couple of years ago, or maybe 1 year ago. What do we do? This in black is the Poisson bracket on M, my non-trivial bracket. Of course, it is not anymore consistent, namely Jacobian identity does not hold if I keep saying that X with P gives delta ij. I have to modify the whole Poisson bracket on this Rn, so at least I have to add this contribution here. I could add also something pp, but we choose to remain simple. It is enough to modify this one. I impose Jacobi identities to this whole bracket, and I get an equation for this unknown gamma, provided this one is a Poisson bracket. So symplectic embedding means that I am considering my Poisson bracket on M, and I am embedding it into a Poisson bracket on this term. I impose Jacobi, and I have an equation for this gamma.
Are you guaranteed that there's a solution to this?
What I am not guaranteed, this has to be complemented with the request that when theta goes to 0, I didn't add it, but when theta goes to 0, this goes into delta mini. I have certainly I do not have uniqueness of solutions. I think I am guaranteed that I have.
So when theta goes to 0, lambda becomes.
When theta goes to 0, everything is this will not be here anymore, this is not here, this is not here, and then you see that this is the solution is a delta. Also when theta is constant, also the Moyal case gives gamma as a delta.
Dirac delta.
Yes. Namely the canonical Poisson bracket between P and Q.
Okay.
Okay? So the goal is to find solutions for gamma.
Lambda is distribution value then. So does that create problems?
Lambda is a tensor.
But it has a
Poisson tensor.
Gamma is just
Gamma is again a matrix.
delta.
Not Dirac, sorry.
Oh, it's a Kronecker.
Kronecker, sorry. Kronecker.
But the Kronecker was going to give me 0 because Kronecker is not antisymmetric.
Gamma will be, this is between X and P, Q and P. Qi, Pj will be delta ij. This is the bracket between X and P.
You don't require antisymmetry.
No.
Okay. The wedge is not antisymmetric.
The wedge is, but I mean, this will, when you only apply this one to X and P, this will give you exactly delta, well, it gives you gamma min E. If I compute bracket of X with P, I get gamma min E.
Yes.
So you get the standard Poisson structure.
Yes, standard one. And delta is compatible both with theta being 0 and theta being constant. Jacobi identity is satisfied. Okay, so provided Sergio Vaccaro is asking something or commenting, making a comment. To include gravity with non-associative and non-commutative star-product deformations on cotangent bundles, a generalization of Einstein gravity, it is more interesting to consider almost symplectic embedding. There is elaborated such a geometric formalism.
I think Sergio wants you to give a different similar.
Okay, if you can give me references to this, I will be happy to read. Coming back to our gauge transformations, once we have these structures, so once we have solved, we have solutions, we repeat exactly what we did in the case of constant non-commutativity, namely we compute, so the gauge transformation is defined again as a canonical transformation. I compute the Poisson bracket up, but now with this new Poisson structure, which includes the bracket on M, and then I pull back it on M. And what I find is this expression. So you see, with respect to the Moyal case, the derivative of the gauge parameter has gained this factor gamma in front of it, which is a delta only for constant non-commutativity. Otherwise, it is clear. So, well, here I simply restate the procedure without resorting to this pullback, push forward, and so on and so forth. And namely, I write everything locally. So locally, this is my phi A, and my gauge transformation is just given by the Poisson per bracket of F with this phi A, evaluated at phi A equals 0. The Poisson bracket has two contributions, one over n and one between x and p, and this is the expression that I get. I stress here that the derivatives are deformed by this factor gamma ab, which is different, let's say, which is a generalization of the Moyal case. So this is the gauge transformation of A, and we can check that the commutative limit, of course, gives back the classical result because the gamma becomes a delta and the Poisson bracket over n goes to 0. So this is the gauge transformation. This contribution here goes to 0 in the commutative limit, and this one goes to delta AR. So I get back the right commutative limit, and I can also check that gauge transformations close. There is a Lie algebra homomorphism between gauge transformations and my Poisson bracket over n. Well, here I say again what happens for the real case, but we already commented on it. Well, here I remark the fact that the constant case is also a solution for the full non-commutative case. We have already seen that this is the gauge transformation that we get in the full non-commutative Moyal case. What about solutions? So we have found solutions for Lie algebra type non-commutativity, namely the first non-trivial case when the Poisson bracket theta is linear in X. Perturbative solutions have been found for more general cases. And about the non-uniqueness of the solution, we have shown that, however, there is a field redefinition which maps gauge orbits onto gauge orbits for different solutions, and then all of them are equivalent in this sense. We will see something about it in a while if I still have time. But I want to go to the field strength because this was for the gauge potential A. What happens for the field strength? So one would expect that a similar procedure works for F, namely in the classical case theta equals 0. F is defined, maybe defined as the Poisson bracket of my two constraints, P minus A, P minus A, with the canonical bracket on the tangent bundle, and indeed I reobtain the usual expression of F. So I want to apply the same here when xp is not 0. I perform the computation and I get this expression here, which seems reasonable because I have my Poisson bracket over M, and I have a deformation of the derivatives. So it seems what it should be. But we found a problem. The problem is that if I go and look at the gauge transformation of F by using the gauge transformation of A that I have defined, I find the right transfer, which will tell me that F is transforming covariant in this approach. But then I have unwanted terms. So the definition of F had to be modified. The modification was first introduced by Kupianov and Sabo in 2021. They actually looked for a solution which was the formation of the F I have just shown. Namely, they write the gauge covariance conditions for F and they find an equation for this tensor R. We did something a little bit different. Namely, we thought we rotated our constraints in terms of which F is defined. F is defined as the Poisson bracket of phi mi phi mi. So
this R that they introduced, it's not a curvature tensor or anything like that.
We do not have an interpretation as a curvature tensor yet. Namely, we do not have a differential calculus which would tell us that F is some D of A. This is something that we are looking for, but we do not have it yet. What we have is this. F was defined as the Poisson bracket of phi with phi. Did I write it? I didn't. Well, yeah, here. If you write this locally, this would be phi mi for Poisson bracket with phi mi. And we have seen it gives this tilde here, which is not covariant. So we decided to allow for a rotation of this phi into the space of constraints. This matrix rho is a function x and a. And non-degenerate because we want to be sure that these two conditions are equivalent. And then we impose that the new F, which is defined as the Poisson bracket of this phi, two of them, be covariant, and we get a new equation for rho. So we have one equation for gamma, which has to be solved for the Poisson structure, and one equation for rho, which has to be found in order for F to be gauge covariant. The nice thing is that for the algebra type non-commutativity, there exist simple, let's say simple solutions. So linear non-commutativity is this object here, this bracket. The two equations for gamma and rho simplify a little bit because now theta is linear in x, so some terms disappear. Of course, we have always to impose this limit here. And then we have found solutions for gamma and rho. The solution for gamma is expressed in terms of Bernoulli numbers. And the solutions for rho is this one. The inverse of rho is related to gamma and A. This notation A hat is a shortcut to include the structural constants into A. So at least for the linear case, we are able to have a U1 gauge theory, which gives back the right commutative limit, which gives a field strength which is fully covariant, and the gauge transformations closed. I think I wrote it before. Shortly, I have two slides. I don't know if I can go. Yeah. I mentioned the Seiberg-Witten map. What did I mean with that? I wanted to say simply that if I perform so any invertible field definition of this kind gives rise to new solutions of the equations that I have shown you. but these new solutions are equivalent in the sense that they map K orbits onto K orbits, and there is a fact that we observe, namely all Poisson gauge models that we have constructed so far for the linear case, for the linear bracket, are all we are able to exhibit transformation of this kind, which connects all of them to the solution that I have shown, and for this reason we call them the universal one. So they can all be reconducted to this solution here with an invertible map. Okay, so here I am at the conclusions. To summarize what I have shown, novel approach to the, here we do not have a fully noncommutative gauge theory, we have a semi-classical approximation, which is based on symplectic embedding. There is a relation between this approach and the L-infinity bootstrap. Indeed, these people started with the L-infinity bootstrap in 2018, and we also did something in the 20s. I didn't have the time, it is a completely different direction. Many applications to linear noncommutativity are now available, among which Kappa-Minkowski spacetime for those of you who are interested in it. What is left? Well, the matter sector. I didn't speak at all about how to make this theory interact with matter fields. For that, we need a covariant derivative, and we do not know yet how to construct it in this approach. Study the dynamics and exhibit solutions. We have some results. We are far from full regime, but what I am really interested at this moment is to understand better the geometry, namely the differential calculus, which is connected with this approach. So, as Denjo was asking, I would like to understand F as the curvature within some differential calculus of my gauge connection. And well, I am working on that, and I have no complete results yet. Thank you.
Thank you very much. Open to questions.
I have a silly question.
Yeah.
It was on your slide 4, I think.
Slide 4.
Slide 4.
Yes, sorry.
Yeah, here. So with the theta matrix, you said that you could always diagonalize this?
In even dimensions, this is constant. This is a constant matrix,
Yeah, okay.
non-degenerate.
Yes, non-degenerate and even, and it will have a 0 in our dimensions.
Yeah. Got it, thank you. Yeah.
You can put meaning. Well, what I meant is that you can put it in a block diagonal form in such a way that it is really the matrix that you have in quantum mechanics.
What exactly is wrong with the approach of modifying the differential operators? I think you called it the Drenfeld twist.
Oh, well, there what you do is start from an operator which is valid in the tensor product of some universal enveloping algebra, which is typically connected to the space-time symmetries. So you have an operator which is acting on the tensor product. For example, it is acting on the tensor product of functions, meaning that in that way you are able to write the star product in terms of this twist. But this same operator can be used to twist any other bilinear map, including the differential calculus. So it gives automatically a prescription to have a differential calculus which is adapted to your non-commutative space time. I don't know if I answered your question.
But does that work? Like, why don't you use that approach?
So you have something like that. Can you see the blackboard? Can you see the blackboard?
No, sorry.
If I write here?
No, but no, I don't think so. Sorry, it's okay. Don't worry.
Is there a way for him to see the blackboard?
There is. It requires driving this device here.
But anyway, the problem of the right commutative limit you also have in that case. So even in that approach, you do not recover, as far as I know, the standard gauge theory in the commutative limit, unless the non-commutative is constant. Again.
Okay, that answers my question. Thank you.
Okay,
I think he hasn't set it up.
Slightly unrelated question.
Yeah.
I think there is proposal probably by Freiberg and Mitchell that you can think of non-commutative geometry as coming from turning on an E field, this Lemon form field. Is that only for constant theta or for any arbitrary?
I think arbitrary theta.
So is also case that corresponds to a particular class of B fields then? If I try to think in that language?
Well, you could think to the semi-classical approximation in that case, and then that would be a Poisson bracket. I mean, the first order of the star commutator is always a Poisson bracket. The contrary, it's not guaranteed. I mean, it is not assured that you can quantize. Formally, yes, but in practice, it's not assured that starting from a Poisson bracket, you are always able to reconstruct a star product. But the quantization process, you can always.
Do we have other questions? Georgia?
Yes.
If I want to define some gauge theory on a manifold which is composed by whose coordinates are both commuting and anti-commuting, such as corresponding variables, is it possible to use this formula?
Yeah, it just means that your theta is degenerate. No problem. The important thing here is that when you do the symplectic embedding, the complete bracket is symplectic. So that is not a problem. Indeed, I think when we do Kappa-Minkowski, for example, or some other the algebra type of commutativity, in some cases we keep time commuting, so it's not Kappa-Minkowski but other cases. We keep time commuting, so that could be a case where one of them is commuting from the other.
If there are no other questions, we can let's thank you, Patrizia. We can retreat for coffee upstairs. Tea.
Bye.
Can you treat the references in?
Yeah, he sent me references.
Mm.